So welcome everyone. Welcome to the next episode of the Hanover seminar series. Today we have Dr. Pete Bettinger, and I don't think he need any introduction. He's well known in the forest management community. He's the Distinguished Professor in Forest Management at the University of Georgia. He is author of multiple books. I can see that you have there are 4 books, at least in academic press. And we use forest management and planning as the course book for our class in forest economics and management. So he has been honored with a lot of awards, and he's a phenomenal educator and inspiration to all who do forest management. I have been inspired by his work and his book a lot. So with this, I'll let Dr. Bettinger speak. Thank you.
Thank you, Rahu. Should I share my screen, I suppose? Does that sound like a good idea?
Yes, please.
Okay. Okay, where did we go? I lost you.
Yeah, share screen.
Sorry, I lost my Zoom. There we go.
Oh, okay.
Where did you go? All right, sorry about that, everyone. Okay, how does that look?
Yes,
Look good?
Yeah, looks good.
Thank you, Rahu, for inviting me to this seminar series, the Hanover series. Thank you, Renee, for helping arrange it. I have to apologize. I can't be there in person because I teach 4 classes this semester, and it's really hard to leave in the middle of the semester and make all the arrangements to for guests and all of that. But Rahu kind of suggested or prodded me in this direction of talking about challenges to forest planning. My background has been in quantitative models to develop forest plans and investigating how they might be able to solve problems faster and easier. In fact, I've sort of spent a lot of time in an area called heuristic programming, which if you're not familiar with optimization, it's kind of like the stepchild to all of the pure scientists, but we like to say with heuristics that we can solve just about any problem that can be quantified. We just don't know if it's the optimal solution when we solve it. So we made some inroads there, and so today I thought I'd share some ideas that some of my colleagues and I have been interested in over the last 20 or 25 years now. And we've seen how computer systems and GIS and databases have all advanced pretty amazingly over the last 25 years to put us in a nice position where we can do things today that were not even possible 10 years ago or 15 years ago. So with this presentation, I'm going to outline, though, 8 areas that I still think are sort of open areas of concern or open areas of challenge to the forest planning. But first, a simple question. I know climate change is a very important issue, and so a little background, most often people don't account for it in forest planning. So the question is, why would someone do that? And so some thoughts here. We might have some important issues that we want to address and acknowledge if we're thinking about developing longer term forest plans, belong a lot beyond 30 or 40 or 50 year plans. And there may be some impacts that might influence land suitability for growing trees and growth rates of trees and other important factors. And since forest planning makes a lot of assumptions about the future, these issues could be important to us. In addition, the probability of some associated events may be affected by changes in the climate, and we may want to recognize those, perhaps as we are trying to develop a guide for people in the field of actions to follow that might lead to a sustainable or resilient system. So managing forests, though, for real world issues of sustainability and resiliency may be complicated by some of these changes to the climate, and so they may prompt us to perhaps acknowledge changes in the climate while we're developing the plans. But humans are funny, and it's humans who develop these plans, and they need good data. They need to be competent, good people. They need to have decent computer systems and this mysterious thing that I like to call organizational support to do a good job at developing plans. But as a result of limitations in one or more of those areas that I just mentioned, most forest plans today are really either very vague in what they're suggesting that would be implemented on the ground, or they're more simple and deterministic because that's the easiest route to go. Doesn't require a lot of assumptions about uncertainty, which I'll come back to towards the end here. So I thought today I would cover very briefly these 8 areas, 8 themes that I see as challenges to forest planning in light of climate change, things that we might think about or address if we were putting together a forest plan to implement in the field, and this forest plan involved a large area and a long period of time, that maybe some adjustments need to be made in some of these areas. So let's begin with shifts in our expectations of land use. Often in the development of a forest plan, it's the land allocation that's put together first. So a land area is divided up into allocations or classes that represent perhaps the better uses of those areas for different goals. This is an area in Turkey that a friend of mine gave to me as an example, where they divided up this landscape. The stands that you see there are, to put it in your perspective, 40 or 50 acres in size each, and they are all given a major use and a couple of minor uses, and so that helps us define the appropriate actions to implement in those areas. And we often build tactical or strategic plans next. Tactical would be shorter, 10, 20, 30 years, and would indicate where to go and what to do of different activities over time. Strategic would be a longer plan, maybe 100 years or more. A little less detail there, but the idea is the course of action sustainable in the long run? And so that's what they want to try to illustrate with that kind of plan. And often today you'll see these two kind of blended together, but again, the first step is the land allocation. And interestingly, we often consider it to be static throughout the entire time horizon of the plan. Just like in this case here, if the plan were 50 years, then these allocations wouldn't change. So the allocation classification doesn't change during the planning horizon. Perhaps it should, based on changes in the climate, and maybe our uses of land might change based on changes in the climate, and also the markets that drive production of different products, they may shift. So, and also again, the development of urban and suburban centers, the outgrowth of people into the wilderness or the landscape. It might change the value of land and perhaps the ability of the land to produce different types of products. So just a few suggestions. I'm going to give a few suggestions after each of the 8 areas, each theme. So perhaps an evolving land classification system might be recognized in the future. And that could be used to help acknowledge and shift around activities across the landscape to recognize that things are changing. Resource vulnerability to expanding human development might also be recognized. I know some folks who have tried to do this around Portland, Oregon, and the expanding metropolitan area out into the countryside may affect the value of forested areas for timber production versus other uses. So those kind of things could potentially be incorporated into forest planning, along with changes in the transportation system as new roads get built or roads get widened or whatever is necessary in a changing world. Second challenge that I mentioned here might be addressed in the future relates to potential shifts in natural ranges of tree species. My example here is bald cypress because to me it's an easy example. It's grown up along the eastern coast and up the Mississippi Valley. But if the climate does change, perhaps its range may also shift, in this case, more to the north. And you can imagine that changes in temperature regimes might also provide more favorable or less favorable conditions for different tree species. So while in the grand scheme of things, these shifts have occurred over long periods of time, perhaps due to climate change over long periods of time, the assumption here might be that as climate change is being accelerated, perhaps we need to recognize these potential shifts in shorter periods of time, perhaps within the time frame of a forest plan. And so for forest planning, alternatives that illustrate these shifts potentially if a property that is being managed is on the fringe of these natural ranges, and the corridors through which migration of tree species might naturally occur might be modeled in the long term to address one aspect of climate change. We'd also need perhaps different transitional pathways or management regimes for different kinds of forests to reflect how they might respond in different parts of the range in which they naturally might occur, a range that might be expanding or contracting. And these different alternatives would then be made available as choices to a planning system. And that's really what planning is to me, is to select the appropriate choices for each piece of land that best meet the objectives of the landowner or land managers, subject to all of the constraints that they find as important. What gets a lot of attention these days in the media are potential shifts in disturbance regimes like fires and insect outbreaks. I think this is a gypsy moth problem on the hill here to the right. And other diseases as a result of changes in the climate. For forest planning, these relatively stochastic events can be difficult to model because we can't really predict where and when they're going to happen way out in the future. We have to make some educated guesses based on historical disturbance regimes. But they might be important even though they are often ignored in forest planning. We might also think about alternative management practices that could be modeled and made available as part of a forest plan. Some of these have been proposed, like prescribed fire and are used, or mastication of wood and removal of it from a site and burning it for energy somewhere, basically reducing fire hazards out on the landscape. So we might examine them or assess them for their usefulness in mitigating some of these natural disturbance issues that might come along. But it is very challenging to incorporate these kind of issues like fire and insect outbreaks into a quantitative forest management model. I've actually tried it. A fire model I developed that actually modeled the spread of fire and the reduction in the tree count and basal area of those areas that got burned, depending on the severity of the burn. And it was very, very difficult to do, and even more difficult to explain, which may reflect in the reluctance of land managers to want to recognize it in their plans. But we may need alternative practices to recognize different options, and we may need to model other kinds of outcomes and evaluate them to complement and assess the attainment of goals, to assess sustainability and resiliency. But all of this does kind of lead to this issue of growth and yield of forests and how they might change as the climate changes. So from one time period to another, a forest is going to have some trees die through mortality, and the rest of them may grow, and some others may appear as ingrowth. And these processes that are modeled within growth and yield models might need to be adjusted to reflect different climatic conditions. And in conjunction with this work, we might have to even go out and conduct some field studies along the fringes of the ranges of tree species to see how they are reacting, if at all, to different climatic conditions. We have to think about when we utilize growth and yield information in forest planning, which we do need, is we need to understand what the forest looks like out in the future. We need to understand how we can reflect warmer temperatures or higher precipitation rates. And if we have a deterministic growth and yield model, like many of the models we have today, how would we modify it to reflect those changes? Will we change the site index slightly, for example, or would we go in and change the growth or mortality models? Or would we need a whole new model entirely, like a process model that folks use, particularly out in the West, to model gaps in canopies and the ingrowth into those forests? So these are some challenges for us with respect to growth and yield, to acknowledge changes in growth processes, the forest dynamics as the climate potentially changes. We probably would need to adjust growth and yield assumptions if we're developing a long-term plan. Justifying those assumptions is going to be difficult to do, but that's our challenge, isn't it? So the fifth area relates to scale. The fifth theme relates to scale, both scale in terms of time scale and scale in terms of the landscape scale. Most forest plans are developed for a specific piece of ground, a specific area. They don't generally utilize information from nearby landowners. I think only once in my career have I seen sort of a collaborative planning effort attempted. And it didn't work very well because people didn't want to share their information. So this is where we are, though. We have tactical and strategic plans. Tactical plans, again, involve a shorter time frame, and they involve more information about where to go and what to do during that time frame. The strategic plans involve longer time frames. But I would argue, given our advances in computer systems in the last 10, 15 years, that these two ideas can be combined into one kind of plan, because really it's the processing of the data and the time it takes to arrive at an answer that forced us to go in those two directions, the shorter plan and the longer plan. So as I mentioned, most plans only consider the resources within a specific property, like the state forest here. I think it's in Vermont. Some may argue that what we do as land managers on our property may affect the conditions on nearby landowners' properties and vice versa. And so perhaps when we think about resiliency, for example, we might have to in the future utilize some information beyond the scope of our property, and also the longer time frames. That's going to be even more difficult because we don't know how the nearby landowners are going to manage their lands, or if they'll even own their lands over long periods of time. So again, these are problematic, and they require some assumptions that are going to be difficult to justify, perhaps. But I think in the future, these are the challenges for the young folks here in this seminar. On a positive note, we have great computer systems today. I remember when I was an undergraduate, there was one PC in the whole college where I went to school. Virginia Tech. One PC. It cost $15,000. Now you could do more with your phone than that computer could do back then. So we are in a good place, I think, with respect to computer systems and algorithms. Even the data is getting better in terms of spectral resolution and the spatial resolution, and also the temporal resolution, how often it gets updated. But again, on a negative side, we generally don't manage or have information beyond the properties that we manage, and data sharing is limited. But we do have new technologies, and well, satellite imagery is not necessarily new, but LiDAR is fairly new, and we can fly LiDAR missions anywhere we want. So as one person with a timber company told me a couple of years ago, they collect information beyond their property's boundaries as a way of spying on their competition. I think there's a nicer way to say that. To get information about other nearby landowners might be important for what we do. One of the hottest topics in forest management is carbon sequestration. You may have heard recently some of the recent news about some of the certification programs having some trouble describing how they verify carbon additionality. I'm not going to get into that here. But in forest planning, within the models we develop, carbon is really just another outcome. And certainly if we can estimate timber volume, we can translate that to carbon. The question is, with respect to carbon markets, is how much of that carbon is additional above the normal practice of a landowner if they chose different management regimes. And it's that part that they can sell generally as carbon credits. So there's one aspect of this where people are interested in simply removing carbon dioxide from the atmosphere, then there's the other aspect that it might provide an additional revenue source for certain landowners. It is interrelated with other issues in forest planning. It's intimately tied to natural disturbances, which we can't predict, which we then may lose that carbon pool, or it may change. And as you will see in a moment, there's a lot of uncertainty in all of this, especially some of these last few things I've talked about, that the additional carbon stored, as suggested by the landowner, beyond their normal practices is really unique and additional, or were they not planning to do those things anyways? Let me give you an example. A landowner around here was approached by a carbon marketer, carbon credit marketer, and they basically told them, we'll pay you a certain amount per acre if you don't cut your trees this year. And so the additionality in their mind was the extra growth over 1 year. But there was no mechanism there to ask the landowner, were they going to cut their trees anyways or not? So there's some challenges there in that other side of the carbon issue of managing the metrics involved and the validation and the verification of it. I think is also an issue, but it's not that closely tied with mathematical programming that I'm kind of talking about here, planning. So some future suggestions with, as it relates to carbon sequestration, we could make assumptions regarding changes in the climate and translate those to potential changes in growth rates, and then that translates to potential increases perhaps in carbon stored in the forest on the stump. We can also perhaps assess some uncertainty in achieving these additional amounts or lesser amounts, depending on how the climate changes, of carbon sequestered through the management practices that we are modeling, and through the growth and yield efforts that we are then using to describe what forests will look like over long periods of time. So again, we could go back to the growth and yield issue from a few moments ago and simply change an assumption about how the forests will grow, and then we can see, well, how much carbon are we going to, extra carbon might we sequester if the climate does change like we expect it to. Seventh of the eighth area of interest, I think, is invasive species management. And these issues might increase over time with changes in the climate. I'm not a forest health expert, but I do recognize the growing concern over plant, like this Kogan grass that's growing here, and kudzu is another example. So both plant and insect spread, invasive species, as a result of changes in the climate, and how those outbreaks or spread might affect the quality of the forest that we manage and the resiliency of that forest to remain healthy. I think we do need more information on the influence of both climate, potential climate change, and management on the spread of invasive species. And I think we need to develop, like a lot of wildlife biologists have done with different wildlife species, we need to develop what I call these functional relationships that link forest management activities like thinnings and final harvests and other things to the spread or the deterrence or the growth of these invasive species. So how do forest conditions change as assumptions concerning invasive species change, and alternatively, how does the status of invasive species change with the implementation of management practices? These are the functional relationships. And how then does climate change affect all of that? So these relationships are important. I don't think we're there really to model them very well within a quantitative forest planning environment. But once the models have been developed, just like a lot of wildlife models, we can perhaps incorporate them directly into mathematical forest planning models. A lot of the fuss in forest management has been made over whether uncertainty has been recognized. I know some colleagues on my hall here in my building at the University of Georgia are looking into uncertainty. It not only resides in the data we use, but in the models that we use to reflect the growth of forests. And it could also be inherent in the functional relationships that we try to develop between management activities and outcomes. So these are all challenging areas, especially when we think about uncertainty, and I hope you don't get too disappointed, but today often they are ignored in most forest planning efforts. They're just given sort of lip service, that it's possible things can change, but we really don't know how to model those at this point in time. So that leads up to this last theme, which is uncertainty. And so there are people today who are attempting to show or illustrate how potential ranges in outcomes due to changes in assumptions of the climate might vary, and this ongoing area of work might be of interest to folks who are concerned about long-term outcomes of forest management. Most forest managers, though, are not data people. They're not technical analysts like a lot of us are, and so they do view uncertainty differently. Sometimes they get a little bit confused about it, and perhaps that's why often it's not really incorporated into forest planning today. Excuse me. We are developing methods. I think this is a new area of work, especially with growth and yield models, to understand how uncertainty in the real world can be incorporated into models which before not too long ago were simply deterministic individual tree models, which had functions that described growth and mortality and other dynamic processes. Well, I've got some final thoughts for you, just 4 more slides. So perhaps we need to continue to push the limits in forest planning, quantitative forest planning, to a point where we can model different forest and landscape scenarios in a more sophisticated manner than what we do today. There are a lot of folks in research at various universities who are working on methods. Usually these are Canadian or American or European universities, but I have some colleagues in China and Turkey and countries like that who are also curious about these advances. And so they're working on areas that we mentioned here. Some of them, I think the evolution is kind of slow, but I don't blame it, because it does require new ideas and new data, new algorithms. And the transition to practice might take a little longer than we expected. Maybe not before I retire, but perhaps within some of your careers. But there are challenges translating potential climate-related changes to relationships that help us understand various aspects of sustainability and resilience, how we can think about those functional relationships between potential management activities and the outcomes of management, and how climate can also alter those trajectories of the forests. I think there needs to be some work done on sensitivity analysis. Maybe this is a way to acknowledge uncertainty, add some stochastic elements into the forest planning assumptions, generate new outcomes, and maybe assess the sort of scope or range of potential outcomes, even though the modeled system is not usually explicitly reflective of the real world system. So we have these other more practical challenges too. We don't have all the time in the world to make a forest plan, although the U.S. Forest Service might argue with that. We generally don't have the kind of data we need to do the very best job we think we could do. There are ways to collect it or develop it, but they might be unreachable given the cost of those. The models that we want to develop a contemporary forest plan might be very complex. And for the people involved in the planning team, it may be sort of out of their realm of expertise to utilize. And so to bring in another expert to do that might also be cost prohibitive. And this may sound kind of simple and dumb, but sometimes it's the computing systems we have that are the limitation. I was asked at one time to provide advice to a certain company about their planning systems, and their planners were complaining about how long it took to generate an answer to a problem when the president of the company comes by and says, what's the answer to this problem? And so they formulate it and they run it, and it takes them almost a day to get an answer. And the simple answer was buy a new computer, because their computer was 3 or 4 generations too old. So one final thought here, last slide. Even though many aspects of forest planning involve a social dimension, which I didn't really talk about much here, there are people involved. And people have their own dynamics. They have to work with each other. They have to negotiate with each other. They have to share data and share work processes and try to all be on the same page. The actual tractability, as I call it, the mathematical difficulty of the problem they try to solve is important. And so as a planning team is sitting around thinking about all the things that they want to acknowledge in a plan, they may be suggesting things that are well beyond what could be modeled. And then the question becomes, what they do, is that good enough to satisfy the decision makers? And if they have to go the extra mile to develop a really complicated contemporary model, will it be user-friendly enough or responsive enough to changing concerns about some of the objectives or constraints of the stakeholders? And again, can they arrive at an answer in a reasonable amount of time? The answer being a forest plan, which provides guidance and direction to the people in the field who have to manage the property of interest. I think with that, Rahu, maybe we can entertain some questions if there are any. Thank you for the clap.
Yeah, thank you, Dr. Pettinger. So yeah, please feel free to, we don't have any questions in the chat, so feel free to unmute yourself and ask questions if you have any at this moment.
Hi, can I ask a question?
Yes.
So the Pete, thank you for great presentation. And I was looking up your website, and your picture was at the Institute of Artificial Intelligence of your institution. And can you give us some idea how we can use the artificial intelligence for the forest project?
Wow, that's a great question. By all means, I'm not an expert in artificial intelligence. So let me sort of set the stage. I'm a professor here in the School of Forestry at the University of Georgia. And since I use heuristics and linear programming and other sort of optimization methods, I was asked about 20 years ago to become a fellow in name in our Institute of Artificial Intelligence, which is over in computer science. And so that institute has 30 or 40 fellows from around campus in various disciplines who can contribute to the training of the artificial intelligence students. And they use one of my classes, it's called Advanced Forest Planning, as a optional class for their students. So I guess in a way, what I do is sort of artificial intelligence, and I also sort of use LiDAR and regression. Some of my postdoc and my research coordinator are working on projects that involve those things. So, Mr. Koyama, I'm not exactly an expert in artificial intelligence, but that's a great question. Thank you.
Thank you.
Thank you. Any other questions from the group? Please unmute and ask.
Hello, Dr. Bettinger. Thank you for the wonderful presentation. I was just thinking about your last slide when you talked about the decision support systems that exist to help land managers and decision makers think through about how to incorporate climate change into their system. Could you please elaborate into what exactly are those decision support systems? Are those some
Sure.
kind of material or some application softwares?
Okay.
Thank you.
Okay, so in forestry in North America, there are really only two commercially available harvest scheduling specific decision support systems. One is the REMSoft system from New Brunswick. Some people call it Woodstock. And that's a linear programming based harvest scheduling system. Universities can get a educational license from them. I don't know if Michigan State has that. It is very complicated to learn and difficult to use. I don't spend a lot of time on it in my classes for that fact alone, because it's just hard to keep everybody on the same page. I think to use it, you would need specific training from the REMSoft people, or maybe there's some YouTube videos that would help. The other system is called Patchworks. And the person who developed that is in Alberta or Saskatchewan. It's a person named Lockwood. He was one of the first people to write a paper on heuristics, simulated annealing heuristics in forestry. And that's a small 1 or 2 person consulting firm that sells the software that he developed. Otherwise, most organizations develop their own models internally, and they don't tell anybody really what they are. I've been asked by several consultants to help them understand how they could do that. Weyerhaeuser asked me how to do it. I'm not sure they really followed any of my advice, but it's just a funny world, you know. Nobody likes to share. Everybody wants a competitive advantage. They want to be able to model over the long term some of the more complicated forest management issues like the adjacency of clear cuts. But they want a system that's their own, that meshes up well with the data and the other information systems that they already have. So that's kind of where we are with forest level planning. There are lots of growth and yield models. There are even decision support systems that a person could use to develop a stand level management regime, but for one stand at a time, not for the entire forest. So that's a good question. Thank you, Ms. Thapa.
Yeah. Thank you. Thank you. Pete. Yeah, we do a little bit of linear programming, but we use Lindo, free version of Lindo. Woodstock is too complicated.
And that's what I use when I teach linear programming too.
Yeah.
It's the easiest one.
Yeah.
To learn what's going on with linear programming.
Yes.
And I think it's really good that a student does it one time.
Yeah.
Because in the future, they may work with people who have to use Woodstock or some other linear programming system. And at least they know the language now. Yeah. We use Lingo too, yes.
So I have a question. Talk about these different climate change scenarios and how we can incorporate that into the forest management planning. So there are these RCP scenarios. Are you aware of any management tool that uses those GCM and RCP scenarios to account for climate change in management plans?
Oh, good question, Rahu. I think right offhand, I know from some of my work, you could say that that's what's happening by changing some assumptions about the historical disturbance regimes of fires. Specific models, though, I think, as I recall, in the Pacific Northwest Research Station of the U.S. Forest Service, they were working on some model called VDDT at one time. VDDT, and it wasn't a spatial model, meaning it's just data. You don't really have the geographic part of it. But I think they were trying to incorporate alternative transitional pathways and mesh them up with historical disturbance regimes of different forest types to try to develop alternative scenarios, long-term plans that better incorporated things like climate change or recognized potential changes in the climate in those plans. So I haven't looked recently for that kind of thing, but you might take a look in the PNW station. They seem to be on the forefront of it. Here in the southern United States, the Forest Service isn't really that much interested in it. You know, they might be interested in fire, but
yeah. Yeah, thank you. Does anybody have any questions or comment, anything?
well, thank you, everyone. I'm honored to have provided a seminar. I hope that you'll find some value in there, and good luck to you in the future.
And